All right, today we're going to play detective and tackle one of the biggest mysteries in the history of science. Let's call it the case of the collapsing atom.
Okay, so let's get right into it because this is a really fundamental paradox. I mean, we all learn in school, right? Opposite charges attract. Positives pull on negatives. So if you've got a positive nucleus in an atom and negative electrons whizzing around it, what in the world stops them from just, bam, crashing together instantly? So, back in the early 20th century, a physicist named Ernest Rutherford came up with this really elegant model for the atom. Think of it like a mini solar system. You've got this tiny, super dense, positive nucleus at the center, that's our sun, and then you have these light, negative electrons zipping around it in orbits, kind of like planets. It was a beautiful picture, and you know what? It made a ton of sense at the time.
But, and this is a huge but, this beautiful model had a fatal flaw. See, according to the physics everyone knew and trusted back then, any orbiting charged particle, like our electron, should be constantly losing energy. It would be giving off radiation like a tiny little radio transmitter, and losing all that energy would make it slow down and spiral inward, right into a death spiral, crashing into the nucleus in like a fraction of a second. Except that doesn't happen, right? Atoms are stable, the universe exists, so something about that model had to be seriously wrong.
And that brings us to our first big clue, or maybe our crime scene, Rutherford's unstable atom. The model says atoms should collapse, but reality says they don't. So what's the missing piece? What's preventing this atomic catastrophe?
Now, you'd think the answer would come from studying atoms more, right? But no. The real clues to solving this whole mystery, they came from a totally unexpected place. A field of physics that was having its own little identity crisis at the time. The study of light.
Which leads us perfectly into our next section, the secret life of light. It turns out, to figure out the atom, scientists first had to wrap their heads around the incredibly weird, kind of spooky nature of light itself. So for literally centuries, physicists were in this big debate. What is light? Is it a wave, rippling through space like a wave on a pond? Or is it a stream of tiny little particles, like a bunch of microscopic bullets? For a really long time, Team Wave was definitely winning the argument.
This energy, this wave, is what we call electromagnetic radiation. And all of it, no matter what kind, travels at the exact same insane speed, the speed of light. Now, we can describe these waves with two key properties. First, there's wavelength. That's just the distance from one peak of the wave to the next. Then there's frequency, which is basically how many of those waves pass by a certain point every second.
And here's the wild part. The light that we can actually see with our own eyes, the whole rainbow from red to violet, that's just this teeny tiny sliver of the full electromagnetic spectrum. It's this massive range that includes everything from really long, low-frequency radio waves on one end all the way up to super short, high-frequency gamma rays on the other. We're practically blind to most of it.
But that popular wave theory, well, it was about to hit a brick wall. There was this one experiment called the photoelectric effect that just completely baffled everyone. It was more than a puzzle. It was like a crack forming in the very foundation of what they thought they knew about physics.
Okay, so here's the puzzle. The idea is, if you shine a light on a piece of metal, you can actually knock electrons right off of it. Now, the wave theory predicted that any color of light should work as long as it was bright enough. You just keep cranking up the brightness and eventually you'll push those electrons out. But that's not what happened. It turned out you needed light of a certain minimum frequency. It had to be the right color or bluer. A really faint violet light could knock an electron out, no problem. But a super intense, blindingly bright red light did absolutely nothing. The color mattered more than the brightness. How weird is that?
And this is where a young Albert Einstein enters the scene. He comes up with this totally radical idea. He said, what if light isn't just a wave? What if it also acts like a stream of tiny energy bullets? He called these particles photons. And here's the key. Each photon carries a specific packet of energy, a quantum, and that energy is tied directly to its frequency. So a single, high-frequency violet photon had enough of a punch to knock an electron loose, but those low-frequency red photons, they were like harmless little ping-pong balls. You could throw millions of them at the metal, but none of them had the oomph to do the job. And just like that, it all made sense. Light wasn't a wave or a particle, it was somehow both.
Okay, so light is super weird. Wave, particle, got it. But how on earth does this help us with our collapsing atom problem? Well, this is where we find our smoking gun. Let's look at section 3, an atom's fingerprint.
So think about a neon sign.
What's happening there? Well, you're basically zapping a tube full of gas with electricity. When you pump energy into atoms like that, they absorb it and jump into what we call an excited state. But they don't like to stay there. To chill out and get back to their normal ground state, they have to get rid of that extra energy. And how do they do it? They spit it back out as a photon of light. Now, based on all the old physics, everyone expected the same thing. They figured if you took the light from that glowing gas and passed it through a prism, you'd just see a nice continuous rainbow. You know, a full smear of all the colors, all blended together, what we call a continuous spectrum. But that is not at all what they saw. For hydrogen, the simplest element, they saw something shocking. Instead of a rainbow, there were just 4 very specific, separate lines of color. A red one, a greenish-blue one, a blue one, and a violet one. That's it. It wasn't a smear, it was more like a barcode. This is called a line emission spectrum. And they discovered that every single element had its own unique, unmistakable barcode of light. It was a chemical fingerprint.
This was undeniable. Think about what it means. The atoms weren't just spitting out random amounts of energy. They could only release very specific, discrete chunks of energy, which showed up as those exact colors of light. And this could only mean one thing. Something inside the atom was forcing the electrons to exist only at specific, allowed energy levels. They weren't free to be just anywhere.
So now we have all the clues. We know light acts like a particle with a specific energy. We know atoms have these unique light barcodes. It's time to bring in our lead detective, a Danish physicist named Niels Bohr, who is about to crack this case wide open.
So in 1913, Niels Bohr puts it all together in this brilliant new model for the hydrogen atom. He basically said, okay, forget the old solar system idea. Electrons can't just be anywhere they want. He proposed that they are stuck in specific, allowed orbits, and each orbit has a fixed, definite energy level. If an electron wants to jump up to a higher orbit, it has to absorb a photon with the exact right amount of energy to make that leap. And when it falls back down to a lower orbit, it spits out a photon with that precise energy difference.
Honestly, the best way to picture this is to think of a ladder. An electron can be on the first rung, or the second rung, or the third, but it can never float in the space between the rungs. It's one or the other. And that's the core idea here. Energy inside an atom is quantized. It comes in discrete steps.
And this model explained the barcode spectrum perfectly. Each specific line of color they saw was just the light from an electron making a specific jump, like from the 4th rung down to the 2nd, or the 3rd down to the 2nd. It also solved the collapsing atom problem. An electron couldn't spiral into the nucleus because there were no rungs in between for it to follow. The lowest possible rung was a stable, ground state orbit, and it simply couldn't go any lower.
So that brings us to our final section, the next quantum leap. I mean, Bohr's model was an absolute triumph. It single-handedly saved the atom from collapsing, and it beautifully explained hydrogen's unique fingerprint of light. But, as you might have guessed, the story wasn't quite over yet.
Yeah, as brilliant as it was, Bohr's model was kind of a one-hit wonder. It worked perfectly for hydrogen, which only has 1 electron. But as soon as you tried to use it for atoms with more than 1 electron, the whole thing just fell apart. It also couldn't really explain the nitty-gritty of chemical behavior, like why some elements are reactive and others aren't. The mystery, it seemed, went even deeper.
So Bohr's model saved the day by putting electrons on these neat fixed tracks, like trains on a railway. But what later physics would show is that even that idea was way too simple. Which leaves us with one last, absolutely mind-bending question. If electrons aren't little planets orbiting a sun, and they're not little trains on a track, then what in the world are they? And, well, that's a whole other quantum story.